So with the choice of zero location, the positive phase shift of zero will be 7.5 degrees of the maximum, while the pole will contribute a phase shift of minus 90 degrees. So if the reduced compensator is used as starting point for lag compensator, the phase margin should be this 5.7 degrees, or approximately they say that it should use to accommodate for extra 5 to 6 degrees. So one important way to complete the design is choosing the location of the poles and zero. There is no fixed way to choose the location of pole and zero, but for a given phase margin, I can clearly find what is the value of R and C I should have for the network. So simplified procedure has been I have given the formulas. You can use that to decide the values of R and C. So a lag component roughly provide the same crossover, but only thing the gain is reduced so that the stability is going to increase. It does not decrease the desensitivity, and it gives you reduced steady state error response. So the response will improve as you add capacitor to your network. One drawback is it employs a zero. So the zero is below crossover, the pole is above crossover. So having the zero below the crossover, it is not going to do us any benefit. So they say that from the root locus, we can ensure that the try to move the zero to the point above the crossover, after the crossover, so that there'll be some benefit you get for the stability of the network. So for that, what we do, we try to shift the zero to some other location by multiplying your response by a cancellation network. So this d of s equal to alpha tau s plus 1 by tau s plus 1. So if you multiply, I am cancelling the zero and then pushing the zero to a point away from the crossover. Okay, so this is more than the value of alpha. The initial value is not zero, but the frequency gain does not go to zero. The initial and final values are different. So the step response evolve from exponentially from initial value to final value. Okay. So there is a pole zero doublet formed by compensating zero to associated closed loop pole. That's what we said. Initially, the system is going to have one zero and one pole. I am going to multiply by one more term, which is also going to have one zero and one pole. So totally, I have two zeros and two poles. That is what is called as a pole zero doublet. Doublet means a pair of poles and zeros, two pairs of poles and zeros. Because the zero is well below crossover, the doublet pole has much smaller time than the inverse loop bandwidth, and the settling time, hence settling to fine accuracy can be much slower than the watt system, which is going to use when the compensator is going to be used. So this is going to be lag.